Hello geometry students, this is 10-3 chords. Our first learning objective is to prove and apply relationships between chords, arcs, and central angles. We will also be finding lengths of chords given the distance from the center of the circle and use this information to solve problems. Our vocabulary today is chord or cuerda. Essential understanding. A chord is the line segment joining any 2 points on the circumference of a circle. The perpendicular bisector of a chord is the diameter of the circle. Example 1. A chord is a segment whose endpoints are on a circle. Why is RS congruent to UT? So we're going to prove this right now. We have R and S, and we have U and T. Why are these two congruent? All right, well, we're going to prove this because I can see two triangles drawn here. I'm going to prove it using the fact that these are vertical angles. And I'm also going to show that these are all radii of the circle and all of the radii are equal in a circle. All right? So we'll say that angle SQR is congruent to angle TQU. That is our statement, and our reason is vertical angles. Because vertical angles are congruent. Then we're going to say that SQ is congruent to QU because they are radii. And we're also going to say that QT, side QT, is congruent to side RQ because they're also radii. And now we can say that SR, which is what we've been trying to prove, S or RS is congruent to UT. So we highlighted because I guess we would have to say that the triangles are congruent before we said that, but I'll fit that in right here. Before this statement that the sides are congruent is that triangle SQR is congruent to triangle TQU because we have a side angle side. And since those triangles are congruent, then the sides that we're trying to prove, the chords, these are chords, that's what we're learning about. Chords RS and UT are congruent because the triangles are congruent and these are parts of the triangle, so corresponding parts of congruent triangles are congruent. And that is our proof for why RS and UT are congruent. And now you can say that that's true for all chords. If, let me see. We're going to get to that theorem in a bit, but if the chords are congruent, then they're the same distance from the center. Why are angles BAC and DAE congruent? And I think we're going to prove that very similarly. So why is BAC congruent to DAE? And I don't think they're vertical angles in this case because they aren't drawn that way. They're slightly off. So how will we prove this? We have triangles. We want to prove that these are congruent. I think we're going to prove it by what we just used. We just learned that, like, if the chords are congruent, then let's see. I see it. Okay. This is a radius. This is a radius. These are also radii. So then we have a triangle with all three sides. No, we have isosceles triangle with two sides congruent and the third side being congruent. So we can prove that these triangles are congruent by side, 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 right? So use red because they gave this to us in red, but side CB is congruent to side DE. That was given to us. Then we can say that, I'm just going to put them all, CA is congruent to DA, which is congruent to BA, which is congruent to EA, because they are all radii. And if that is true, then we can say that the triangles CAB and triangle EAD are congruent because of side, side, side. And if that is true, then the angles have to be congruent because angle BAC and angle DAE are corresponding parts of congruent triangles are congruent. So we have our statements and reasons. And if it was in two columns, we would just separate these statements from reasons. Now that we've proven those, we have some theorems that are going to say the same things, but we don't have to prove them again. All right, the first theorem, theorem 1. If two chords in a circle or incongruent circles are congruent, if the chords are congruent, then their central angles are congruent. And that's the one that we just proved. Secondly, if two central angles in a circle or incongruent circles are congruent, then their chords are congruent. All right. So they've said this two ways. This is the theorem, and this is the converse of the theorem. So they're saying if these are congruent, then the angles are congruent, and then vice versa. If the angles are congruent, then the chords are congruent. This next theorem says if two, let me see, arcs, we did not prove this one, but if two arcs in a circle or incongruent circles are congruent, then their chords are congruent. And then vice versa, the converse. So this one is the theorem. If M and N, that would be from here to here, and P to Q are congruent, then their arcs are congruent. I mean, their chords are congruent. If the arcs are congruent, then the chords are congruent. If two chords are congruent in a circle or in congruent circles are congruent, then their arcs are congruent. When you're ready, turn your page. And yet another theorem, and this one, there is an interactive for it, so I will put that interactive in your Canvas so that you can practice it. This one is saying if chords are equidistant from the center of a circle or the centers of congruent circles, then they are congruent. The second part, it's like we're not really going to see this one, but if they showed two circles with chords and they showed parts of it being equidistant, then it would apply, but that just kind of makes it longer. If you just know the first part of it, that's good. So this is the picture of the theorem, and you can see SE and SF are right here. SE and SF. That's how far the chords are from the center. If those distances are congruent, then the chords are congruent. The converse says if chords in a circle or in congruent circles are congruent, then they are equidistant from the center, or centers, if there are two. And that is the converse, which is pointing here. So it's saying if the chords are congruent, then the distance from the centers are congruent. Example 2, we're going to write a proof. Write a proof of the theorem which states that if chords are equidistant from the center of a circle or the centers of congruent circles, then they are congruent. All right, we're going to draw a circle. I'm going to cheat because I have the ability to draw a circle on my iPad perfectly. I'll give you compasses if you'd like. We have the center. And I want to draw what it's saying. So the two chords are equidistant from the center, so kind of like what we have above. So I'm going to draw some whiskers from the center. And then I'm going to draw the chords. I think it has to be like in the center of it though too, so I don't know if this is gonna look perfect, but I'm gonna do my best. So how would we prove that these are equal? I think I want to do it with triangles. I had to redraw my lines a little bit to make this work because they weren't quite perpendicular. So what I'm going to do is I'm going to draw a dashed line to the center. This is the radius of the circle, and it also touches the chord that I drew. So that red line that I just drew, I'm going to label it A, B, and C. AB is a radius of the circle because it goes from the outside to the center, and that's the definition of a radius. So side A is congruent, or side AB is congruent to side CB because they are radii. Okay, so we have a statement and a reason. Then this is 90 degrees, and that's just given because it's equidistant, so we can assume that. We need some more letters, so we'll call this D, we'll call this E. So angle CDB is congruent to angle AEB, because they're 90 degrees, and that was given to us by the fact that it's equidistant from the center. It just has to be when you draw it like that. What else do we need to prove? So we're proving this triangle. This was also given to us right here, that these are equidistant. So DB is congruent to BE, given as equidistant. And now we have three parts of a triangle. We have a side, angle, and a side, right? So we had the A to B, which was right here. That was because it was the radius. And C to B. So we can, instead of saying angle side side, which we can't, right, because there's no ass in geometry, no angle side side, we can use hypotenuse leg. So we were given a hypotenuse of a right triangle, and we found a leg of the hypotenuse. So that means that triangle CBD is congruent to triangle ABE by hypotenuse leg. And what does that get us? Well, then that tells us that from this side of the triangle, A to E is congruent to side CD by corresponding parts of congruent triangles are congruent. But we're still not done. But we do know that that cut the line, the equidistant line, the black line, cut this into equal parts. Because that was a perpendicular bisector. So I'm going to just come on over to this side because we have space. We can say that we need another letter. F and G. So AF is congruent to C. We're skipping a step, but I think it's okay for this level. No, it's not. We're gonna have to say that part. So we're gonna say that DG is congruent to EF because of the perpendicular bisector. So it's there. I'm missing a step still. It's just 2 steps. DG, which is on this line, is congruent to CD. We have to say that first. Getting ahead of myself. By definition of perpendicular bisector, but since that's the same thing on the other chord, A, E, and EF, I'm going to say them at the same time because that's the same reason. AE is congruent to EF, and the reason of that is definition of perpendicular bisector. Now we have to say that we've already said that AE and CD were congruent. So now we have to say that CD plus DG is equal to CG. And the same thing on the other side. Piece AE plus EF is congruent to AF. And the reason for that is segment addition. Now by substitution, if we substitute in the pieces from above, then we can say that CG is congruent to AF. So I'm just saying a bunch of things and that's allowed. This was by substitution, and then that proves it. Lots of steps. Okay, so let me just kind of highlight all the steps that we had. 1, 2, 3, 4, 5, 6, 7, 8 reasons before we got to our conclusion. Nice job following along with that proof.